So last class we talked about the greedy method for computing the best fit subspace. Right, and this also led us to principal components. And finally, we started discussing the low rank approximation problem. Okay, so today the goal is to kind of so far we describe the problems and describe some high level algorithms. High level, by high level I mean that if we can solve the first principal component, then we can do the other stuff. And today we will finish it and show that you can actually solve all of them by a single magic bullet, which is going to be the singular value decomposition. And then we'll start talking about how to compute it using something called the power method, and why power method is so useful compared to other things. Okay, and few announcements. First, homework 2 is online. It's due next Monday at 10 p.m. And remember, exam 1 covering lectures 1 through 9, basically until last Monday, is next Wednesday. Okay, it's in class, 1 hour 50 minutes, and it'll cover lectures 1 through 9, and you can bring 1 page of notes. Okay, so that's about the only thing that you can bring. It's not open book or open notes, but you can bring 1 handwritten page of notes. Sure. Okay. I don't think it helps that much because it's not like an exam where you would review formulas or something. Okay. The main thing, in terms of preparation is to go through the homework problems, understand the ideas behind them, right? Not the exact things, but even the content. It's really going to be a test of, okay, did you understand the main intuition, main conceptual idea behind all of these algorithms, right? Those are the things that are the most important. And that's what at least I want to test. How successful I am, you'll tell me later. Okay? All right. And as I said before, the previous year's exams, all of them are available, but they are of a little bit of a limited use because the format has changed, some of the content has changed. So just keep that in mind. Okay. All right. So today we're going to talk about how to solve the 2 things that we've been working on, which is best fit subspaces problem and low rank approximation. And for that, there is this remarkable thing from linear algebra, which has been known for many years, really, like centuries, well before things became important for computational reasons. And this is singular value decomposition. Okay, I'm just going to write it formally. Maybe some of you have already seen it, or things like that. Something like eigenvalue decomposition is similar. So let me just state it. Then we'll see some quick examples and see how it connects to the problems that we have. Okay. So singular value decomposition, or SVD for short, is one of the most sort of important operations in numerical linear algebra. And it says that any matrix, no matter what it is, can be written in the following way. So I start with the matrix X, which has n rows and d columns. I can always factor it as a matrix U, which is n by R, a small matrix in between, usually denoted sigma, which is R by R, and then another matrix V, which I guess should really be this one. Okay, we write it as V transpose. Okay, so this is R by R, this is R by D. All right. So if you multiply them, you can see that you'll get an n by d matrix, which matches the dimensions that you want at least. Okay. So if you ask me for such a thing, factorization, of course, you can come up with many, many factorizations. But the key thing with SVD is that it says that there exists a factorization with some very, very special properties. Okay. So what are the special properties? The first one is that the entries of the middle matrix sigma are 0 on the off diagonals. So sigma is a diagonal matrix, and the entries along the diagonal are all non-negative. Okay. All right. So that's first thing to keep in mind. So first, sigma is a diagonal matrix with non-negative entries. Right. And what else do we know? So the other two properties which are also very useful are that the columns of U are orthonormal. Okay, meaning if I take any two columns U here, which are like, let's say, R of them here, their inner product is actually 0. It's a distinct. And if you take any single column, then its norm is 1. Right. So another way to write this is that if I look at U transpose U, this matrix is the identity matrix on R dimensional. Right. And the same thing also holds for V. So columns of V are orthonormal. So V transpose V, once again, is identity. Okay. So we have that, X is U sigma V transpose, where each of these properties holds. Okay. And just by definition, the rank of X is at most R, because I'm giving you an explicit factorization as product of 2, or in fact, 3 matrices here, where each one has rank at most. Okay. All right. So it takes a little bit of work to prove that such a factorization always exists, but it exists. All 3 properties hold. And just to take a quick example, let's say my matrix is I mean, this is a silly matrix, but if I want a singular value decomposition of this matrix, what can I do? I can just write this as identity times, in some sense, you already have the same format, so we are good. Okay. So I have these as the singular vectors, singular like U, V, and this is sigma. All right. Okay. Now, how about something like, let's say, what would be a factorization here? I can't use the same thing as I did earlier, because even this is a diagonal matrix, it has a negative entry. Whereas in SVD, we require that the entries of sigma be non-negative, right? So how can I get around this? So what would be an SVD then? the only thing that you need to really do is to, I can still put identity here. The natural guess is to put 0, 2, but then you put a minus 1. Okay, so this would be an SVD. So here the columns are orthonormal, sigma is non-negative, the columns are orthonormal. Okay. And as stated, this decomposition, can it be unique? Is it unique? No, right? Even for this specific example, it's not unique. I can write this still as okay. This is also a valid singular value decomposition. Okay. You can also do even sillier things. For example, I can have I can permute things. No. Okay. So, the ordering also can change. I can change these things and these things so that I get 2 and 1. Okay. So there, it's not unique in general, but typically to get some sort of sense, when you write down a factorization, we ask for a factorization like this, where the values in sigma are decreasing down the diagonal. Okay, this is just N4 so that we have some sort of agreement on how to write it. Okay, so I'm going to assume that sigma 1, 1 is greater than or equal to sigma 2, 2, greater than or equal to sigma 3, 3, and so on. Okay, the first three properties are fundamental. The last one is just convention. Okay. All right. Maybe just to be clear, why don't I write it down? Just 2, 0, 0, 1. Okay. You can check that this product also equals this product. Okay. Yeah. Yeah. I mean, it's not required in the definition, but ideally you would write it with smallest rank possible. Okay. So that's what in some textbooks and so on, they usually require this to be n by n, and sigma is allowed to be like, again, like an n by n matrix with zeros. You can do that, but that seems a little wasteful. In fact, for numerical linear algebra, it's wasteful. So this is what we're going to do. Okay. So you can assume sigma RR, for example, is greater than 0, right? But it's not strictly required. Okay. All right. So why is SVD showing up here? There's some something was defined in like the 1800s by Jordan or whoever that was, and suddenly we're talking about it 200 years later. Why? Okay. And SVD has many properties, but the two magical properties that are most useful for us are the following. Okay. So now we've written the sigma in a way so that you have this ordering, right? Okay, so maybe, right? So this is a diagonal matrix, but in addition, we have sigma 1, 1, sigma 2, 2, so on. We have the ordering. Okay. Now, if you look at the rows of V transpose, so let's call them vectors V1 transpose, V2 transpose, and so on. Okay. The two magical properties which require proof, and the proof involves some linear algebra, especially Courant pressure theorem or something like that, are the following. The first one is SVD solves the principal components. It actually gives us the principal components. Once you order the sigma this way, V1 is the first principal component of X. Okay. So we define the principal component without any factorization. We just said we wanted a vector which maximized X times V norm squared subject to the norm of V being 1, right? And it turns out that if you know the SVD, V1 is the first principal component of X. Okay. And V2 is the second principal component. Okay, maybe I should say A because sometimes it might not be unique. Okay, and so on and so forth. So Vk is kth principal component. So if we can compute the SVD, we would be solving the best fit subspace problem for sure, right? How do you prove this? This requires some work. In the homework, in the next homework, you will prove, some version of it, at least maybe V1 and V2, but it's not too difficult. It just involves some linear algebra manipulation. Okay. All right. So meaning SVD solves PCA. You want to compute the principal components for dimension reduction or whatever else you wanted to do. If you can compute SVD, you're done. Okay. So this is the first magical property. The second magical property is that it also solves our other problem that we've been talking about. And this is the Eckart-Young-Mirsky theorem from 1936. Right? So the Eckart-Young-Mirsky theorem says that suppose I have some matrix X and I want to find the best rank K approximation. Whatever your K you have, like maybe 10, 20, 30. Then if I define the matrix Xk, which is, you compute the SVD, but then only look at the first K things. So U1 up to UK, and then sigma 11, sigma 22 up to sigma KK. Okay. So R is less than or K is less than or equal to R, and I'm only taking the first K columns here and the first K entries in sigma, and similarly the first K entries in the V. Okay. Is the best rank K approximation to X. Okay. So SVD solves both problems, and in fact, this also shows that principal components are fundamentally connected to low rank approximation. Okay. So one bullet solves both of them. SVD solves PCA low rank approximation. Okay. So if you went back to the Netflix challenge, then to beat their baseline by 4%, remember 10% was $1 billion, so 4% should have been a big deal. But that's just like one line of code because SVD has been known for a long time. It's been implemented for a long time, right? So you just had to compute SVD after doing some pre-processing, and you would have solved or gotten a 4% input. Okay. All right. So that's the connection between SVD and these other problems. Now the question is, okay, so far it almost seems like we are just redirecting our question from one question to the other without coming up with new algorithms, right? So now we're actually going to get a new algorithm and solve the problem. Okay. So how to compute SVD. Okay. And there are different ways to compute SVD. But to start with, let's see how we can compute just the first sort of principal component. How can I compute this V1, sigma 1, and maybe the first column here, right? Once we can do that, it turns out you can still use a greedy approach. Or if you're a bit more sophisticated, you can actually come up with an algorithm which computes all of the things at once. Okay. But sometimes it's more important to be able to compute one at a time, or maybe 10 at a time, or 20 at a time without having to work with a full SVD. Right? Like, for example, if you look at the Netflix challenge dataset, the matrix is so big. I'm not interested in the full SVD at all. That's way too expensive for me to compute. I just want to compute the best rank 30 approximation. So that means I only need to compute the first 30 sigma 1, sigma 2 up to sigma 30, right? And then V1 through V30. How do we compute them? We'll see how to compute them one at a time, okay? To do that, we'll just sort of follow the arithmetic. So we have U sigma V transpose, and sigma has this decreasing order. And let me write down this matrix product in a slightly different way, which is more illuminating for designing algorithms. Okay, so we have this R column vectors UIs, which are all orthonormal to each other. And we have this R vectors V1 through VR, which are all also orthonormal to each other, right? So one way to interpret this matrix, if you expand it out properly, is that when you multiply them, really, the first column here only gets multiplied with the first row in this V transpose and with this. Okay, that's how matrix multiplication actually works. Okay, if you expand it out, then like the second column would be like this, and so on. Okay, so one other way to write this down is that this is just sigma 1 times U1 V1 transpose plus sigma 2 times U2 V2 transpose, and so on. Okay. So just for shorthand, instead of saying sigma 1 every time, I'm just going to write sigma 1. Okay. So what we have is that, okay, so X equals sigma 1 times U1 V1 transpose plus sigma 2 times U2 V2 transpose plus so on. Okay, so that means to compute the SVD, I need to find vectors U1, U2 up to UR, which are all orthonormal. Vectors V1, V2 up to VR, orthonormal, and the sigma i's are non-negative, such that this identity holds. As long as this is true, I have computed the SVD. Okay. And, as we discussed already, this V1 here is the first PC, or the first right singular vector. Okay, this was something that we already talked about. And it's called the first right singular vector because, the u would be the first left singular vector and so on. Okay, so u2 would be the second singular vector, and as notation, typically we say sigma I equals ith singular value. Okay, so the factorization might not be unique, but the singular values are actually unique. Okay, so once you order them, the highest one is called the first singular value. You can have multiplicities, that's fine, but there's a first singular value, second singular value, third singular value, and so on. Okay, all right. So how can I get such a thing? So to do this, what we are going to do is kind of play around with this x to get a form that will help us derive an algorithm. Okay. So the first property that we will use is that suppose I compute x times vi. What do I get? Maybe let me write it down this way. Okay, so x times vi is sigma 1 times u1 v1 transpose plus sigma 2 times u2 v2 transpose plus so on, sigma r times ur vr transpose times vr. Okay. So what do you think will happen when I multiply vi with this product? Any guesses? Well, at the very least, I can expand it out. And if I expand it out, I get v1 transpose vi here, sigma 2 u2 times v2 transpose vi plus so on. Okay. And the reason singular values are really very useful is, of course, that the vi's are orthonormal, right? What does it mean? All of these inner products are 0 unless the I matches. Okay, so that means that this is equal to sigma I times u. Okay, so basically you get sigma times iui. So recall columns of V are orthonormal. So Vj transpose Vi equals 0. J is not equal to I. Okay. Good. The second thing is, you can do the same calculation once again, but with the use, and get ui transpose x is sigma I times Vi transpose. So almost looks like kind of, if you know eigenvalues, that's what it looks like. In x times v equals lambda times v, that's like an eigenvalue equation. This has a similar flavor. Of course, it's not a symmetric matrix or not even a square matrix. So you get something different. X times vi equals sigma I times ui. And ui transpose x equals sigma I times vi. All right? Okay. So same as above. And the third thing that we can see immediately from this is, so let's say I give you the vector vi. Someone tell me, okay, here's your matrix X, here's the ith singular vector vi. Can you tell me what the singular value is? Norm of xvi, right? So that's actually why we're doing it. Like to compute the singular value decomposition, I'm just kind of playing around these equations to see what we can compute immediately and reduce it to the thing that we had to solve minimally, okay? So in some sense, there are three unknowns in SVD. You have u, you have sigma, you have v, right? But the point of these identities is that they're saying If I know one of them, I can figure out the other two. Okay. If you give me the V's, I want to say I can figure out the U's. Why? I can multiply it like this. I'm basically figuring out the U's except for the scaling factor, right? But how do I get the scaling factor? You just compute the norm. So sigma I is norm of X times V. Okay. And this is because, by property 1. So X times Vi equals sigma times Ui, and Ui is a unit vector, right? Okay. So in conclusion, if you give me the V's, I can figure out what the sigmas are and what the U's are, right? So that's what we are going to try and do. If we compute V1 through Vr, we can compute sigma 1 through sigma r, comma U1 through U1. Okay? All right. So now there are many methods to compute SVD. In fact, there are methods to compute full SVD, which are numerically stable and so on. And the main theorem in this space is that I can compute full SVD in time that is O of D times n squared. Okay, should really say, think of it as min of O of 1 times min of D times n squared or n times D. Okay, you can do one of the two, whichever. If n is bigger, then you do this. If D is bigger, you would do this. Okay, it's kind of cubic time, right? You can also get it in matrix multiplication time, but it's a completely different story. But the point is that this is computing all of the singular vectors. It computes everything in one shot. Okay, but it's very expensive. The cubic time is okay for small matrices. You can play around with NumPy and see how big a matrix you can compute the full SVD for. It'll start getting stuck pretty much at like, maybe even 10K by 10K, depending on what laptop you actually have. Okay, and it definitely won't scale to something like the Netflix challenge dataset where we have 500K N and D is like 17K. Okay, so even to write down a full matrix will be way too expensive, right? But we don't need the full SVD for computing or kind of to apply to the Netflix challenge. I only need the top things, right? So that's the question that we're going to ask and answer. Can we compute the first 30 singular vectors easily? Okay, I want to compute the first 30 without having to do this whole thing. All right, and fortunately, we can actually do that. And the most popular method for doing that is what's called the power iteration. Okay, so the punchline here should be that I can compute the first singular vector much faster than computing all of the singular. Okay. In fact, in amortized cost, it kind of really matches what you're doing for full SVD. Okay, you'll see that we can basically compute the first singular vector in a time which is roughly n times. Okay, assuming there is some separation and there's some condition number kind of separation. Okay, whereas this bound, the ND square, doesn't need any such assumption. Okay? We're going to assume something and get some kind of approximate result, but that's well and truly enough for many practical applications. Okay, and it's a win. Yeah. Yeah, basically. If the matrix X has full rank, then there will be, orthonormal matrices. Like, uh, but even otherwise, computing it up to the rank of X, right? Beyond the rank, it doesn't matter whatever else you put. Okay, does it make sense? Right, but it's giving you a lot of other stuff which is not at all useful there. It is doing it, but I think when you the singular values will be 0, so it's not meaningful. Those things are not very helpful at all. It should definitely only compute it up to the rank, even if interested in full SVD, right? For example, if you go back to this equation, where did it go? Yeah, so once the sigmas become 0, like that thing is not showing up in X at all, right? So it's just giving me a basis which is perpendicular, which is kind of the 0 space, the null space. If you want the null space, maybe for some applications you do, then it is helpful. Okay, then I can imagine it being useful, but otherwise, okay. All right. So we're going to see that we can compute the first singular vector much faster than computing the whole thing. And then you can generalize it to computing the first 2, first 3, and the first 30 as well. Okay. So let's focus on computing the first singular vector. So again, our entry point will be this identity. Okay. And so I'm going to write down something for y, which is X transpose X. Okay. So let's work under the assumption that so we're computing the v vector. So we want the d-dimensional things. So let's compute X transpose X. And for whatever reason, I'm just going to write it down. Now, what is X transpose X? This is U sigma V transpose transpose times U sigma V transpose. Okay. And the transpose operation reverses things. Okay. All right. So now, so I have the matrix V, the diagonal matrix sigma, U transpose U, sigma V transpose. Right? But what can you tell me about this matrix, U transpose U? It is identity, right? So we know that U is orthonormal matrix. And in fact, that's how we defined it, defined SVD. So that means this is just, so U transpose U is identity, so it will go away. And what I get is just V sigma squared V transpose, right? So if I once again write it down in this notation that we've been using, then I have V1 up to VR. I have sigma 1, sigma 2, sigma r. Now, the square of a diagonal matrix would just square the entries on the diagonal. Okay, right? So you have zeros here, and then I have V1 transpose up to VR transpose. Okay. And just as before, this once again simplifies. Right? So I can match up how matrix multiplication works. And by doing so, I can conclude a simpler form for this product. Okay? By using the same argument as before, I get y is just sigma 1 squared times v1, v1 transpose plus sigma 2 squared times v2, v2 transpose plus so on. And it turns out, this is a much better matrix to work with because it's symmetric and it's a square matrix and so on. Okay. All right. So we just derived some other identity involving the x, but what do we do with it? So let's say I look at y squared now, which is y times 1. What do you get then? Any guesses? Well, y was v sigma squared v transpose. And then v sigma squared v transpose. Okay, I can regroup these things as v transpose v is identity again. So that's going to disappear. Okay. So by the same sort of expression, I get y squared is sigma 1 to the 4 times v1 transpose, sigma 2 to the 4 times v2 transpose, plus so on. Okay. So what's happening here is that every time, kind of I take a power of y, the v's are not really changing. It's just the sigmas are getting raised to higher powers, right? Because they're orthonormal. Okay. So, I'm not going to do this again, but if I compute y cubed, you get the same thing again. You get v times sigma to the 6 times v transpose. Okay. So meaning this is going to be sigma 1 to the 6 times v1 transpose plus sigma 2 to the 6 times v2 transpose plus so on. Okay. So overall, I get this identity, which is if I take this matrix Y, raise it to the power L, then this is just sigma 1 to the 2L times v1 transpose plus sigma 2 to the 2L times v2 transpose plus so on. Okay. We're deriving some expressions, we're manipulating these things. It still doesn't seem like it's helping us compute the algorithm, right? So the one thing to keep in mind is that we don't know what these VIs are. That's our goal to compute. But we have complete handle on Y. At least for now, I'm giving you the entire matrix X, so I can compute the entire matrix Y. Okay. We'll talk about efficiency, how you can, maybe get around even computing that. But let's, I'm given you X. So I can compute y, which is x transpose x. Okay. At the very least, I don't know how to compute these VIs, but I can compute y to the power L. Okay. But this is some progress towards computing V's. Why? Any guesses? Exactly, right? So in some intuition, like just for scaling purposes, suppose sigma 1 is 1. Okay. And sigma 1 is the highest one, and let's say sigma 2 is 0.8, and the rest are all less than or equal to 0.8. Okay. Now what happens as I keep on raising this to higher powers? I get y to the L is basically 1 to the 2L times v1 transpose plus 0.8 to the power L times v2 transpose plus so on. Okay. And sigma 3 and so on, they're even smaller than 0.8 potentially. Oh yeah, 2L. Okay. So what does this mean? As you increase L, If I compute, for example, y to the 10, this is like 0.8 to the power 20, which is a tiny, tiny number. Okay. So as I increase L, the contribution of everything else is just disappear. Okay? So that's why it's called power iteration. By just simply powering y, I'm magically picking out the first singular vector. Okay. So that's the intuition. We'll make it formal in a second. So as L goes to infinity, y to the L really goes to V1 transpose. Okay, makes sense. So in some sense, y to the L really looks like a rank 1 matrix. Okay, so if it's V1 transpose, it's essentially rank 1. It's very close to a rank 1 matrix. Not exactly rank 1, but all of it's rank 1 plus some things which are exponentially smaller. Okay. All right. So now here comes, we have an idea that if I keep computing this y to the L, then I do get, I converge to the first singular vector, right? This V1 transpose. So from that, I can peel out the V1. It's just like the first column or something. Yeah? Right. So we'll get to that in a second. Let's just work with this assumption, and then we'll see what we can do. Okay. So basically, to maybe just to jump ahead a little bit, if sigmas are the same, in some sense, there's no unique solution for what's the first principal component, right? So what will happen then is that you'll find a principal vector. So if sigma 1 and sigma 2 are exactly 1 and sigma 3 is 0.8, you'll converge to something which is in the span of the first two things and still achieves a, it corresponds to singular vector 1, singular value 1, but the rest will die down. Okay, so wherever there is a gap, you'll pick out the, the largest one. Okay, we'll talk about that in a second, right? So the idea now is to keep powering this y's, and then somehow that will give us V1 transpose. Okay, but let's think of this V1 transpose. What does it look like? It's a square matrix, okay? And every column is some number times V1. Okay. So remember, we don't have access to the V's. We only have access to Y. We raise it to a high power, we get something approximately rank 1. But how do I pick out V1, which has to be unit norm? Right? So how can I pick that out? Any guesses, suggestions? There are many, many different ways, so just tell me one. I have like a rank 1 matrix, but I want the rank 1 factorization. I can just maybe the diagonal entries, but you still, there may be squares there, right? You can do the diagonal or even just the first column. Or its first column is a bit easier, right? Because first column is proportional to V1, right? But we know V1 is norm 1, right? It is a unit vector. Does that make sense? First column. Okay. So that means, if we look at the first column of y to the L and normalize it, we should, or normalize it meaning scale, we should converge to V1. Okay. Which is the first right singular vector, the first principal component, and so on. Okay. So that's, the basic template for the algorithm, right? It's a very simple idea. The idea is compute y to the L for some large L, let's say L equals 100. And then compute the first column, or extract the first column really. Okay. So one way to extract the first column is, just to, hopefully why I'm writing it this way will become clear, is to multiply with the vector, which is 1 in the first coordinate and zeros everywhere. Right? Okay, so let's, this is called the vector. Let's call it E1, vector with 1 in first entry, zeros elsewhere. Okay. So of course, the first column is nothing special. You could have chosen the second column, you could have chosen the third column. All of them are proportional to V1. So you could have picked any particular column. Right? So here we're just picking the first column just for convention. Okay. And then you have to output V bar divided by the length of V. Okay. At least in the limit, as L becomes larger and larger, this is going to converge the first principal component. That's what our calculation suggests, as long as there is a gap between sigma 1 and sigma 2. Okay? All right, makes sense? Okay. We're basically done, but anytime you see something like this, you should think about, okay, is this the best way to implement this algorithm? So we have a template, we have a pseudocode, but is this the best way to implement this algorithm? Okay. Well, what are we doing really? We computed the matrix Y, and then we're multiplying it with itself L times. Okay. And then we're multiplying with this vector E1. Okay. So if I ask you to compute this, how would you compute it? You would go from the right to left, right? Multiplying two matrices is super expensive, but you're not really interested in y to the L. You're only interested in what happens when I multiply y to the L with this particular vector, right? So I should not ever do this computation like this. I should really do it like this. Okay. What's happening here? I multiply the matrix with a vector, and then matrix with a vector, another matrix with a vector, and so on. Okay. So we're just using associativity. The same algorithm, y to the L times the vector E1. I'm just writing it from right to left. Okay. That would be much faster because I'm not multiplying matrices anymore. I'm only multiplying matrices with vectors, which is much, much more efficient. Okay. So that's power iteration algorithm. Okay. So we keep getting vectors, vector, and so on. All right. So let me write down the algorithm, which is power iteration. And I'll call 1.0 because we'll make it even better in a second. Okay. So the first step is compute y, which is x transpose x. Remember, we are given x and we want to compute the first singular vector, first principal component, and the first right singular vector of x, right? And then for t equals 1 through L, maybe we said, okay, V0 is E1, and Vt is y times Vt minus 1. Okay. So I start with E1, multiply it with Y, and then multiply it with Y again, multiply with Y again. Okay, I just wrote it in this as a loop, basically. Okay. And the final output is Vt divided by the norm of V. Okay. Any questions about what we did here? Right? Yeah. Yes. So that's a good point that, what if the first column is actually 0? Okay. So we had to fix for that. But the thing is, how do you know which column is non-zero? We don't know, right? Because that means I would have computed Y to the L, but I don't want to multiply matrices at all, right? Multiplying matrices is like a factor of 20,000 worse if your matrix has 20,000 columns, right? So I want to avoid it at any cost. Okay. So like, for example, as you're saying, what if Y itself looks like this? For whatever reason, somehow I ended up in a situation where the first column was 0, then it doesn't mean the first principal component is 0 because there's still non-zero entries here, but I'm extracting the first column, so I'm stuck. Okay. So what's the fix for that? We don't know which column is going to be non-zero technically, so you have to be a bit careful. Okay. So the idea is to just pick a random vector instead of E1. Okay. So here we started out, in some sense, you can think of it as our initial guess is E1, and then we're updating our guess. We're going to start with a random vector as our guess. Then it's kind of unlikely that we'll be so unlucky. Okay, and you can work that out as we will in a second. Right? So that's point number one. We can fix it by choosing a random sort of starting vector. The other thing is, do I even have to compute this? As I said, I really don't want multiplying matrices. I hate it. But here I'm computing it. But do I need to? No, right? Because I'm still only interested in X transpose X times Vt minus. Okay? So I can use the same trick again. And this leads us to the full power iteration algorithm. So power iteration is the following. So the input, just to recall everything, is some n by d matrix. And the output will be a vector V, unit vector, that is close to the first right singular vector. Okay, and we will quantify how close it is and what sense is it close and so on in a second. Okay, so here's the full algorithm now. The first step is pick a V0, which is a random vector. A random unit vector of unit length. Okay. And then for t equals 1 through some L, you define a vector which is X transpose times X times Vt minus 1. Okay, so I compute this. And, here I'm computing all of this, like Y to the L times Vt, and then normalize it. Okay. But that's not a very good thing to do when you run things on a computer. If I multiply 2 to itself 100 times, like 2 to the 100 divided by 2 to the 100, what do you think you'll get? You'll get a floating point error. You'll get some junk. Okay. So you need to kind of address that. So what's one way to fix it? Yeah. So you should normalize after every step, or maybe every few steps, but let's just do it after every step. Okay. So let me introduce this, intermediate vector zt, and then vt is just zt divided by z. Formally, it's basically the same algorithm, but implemented in a way so that you don't run into like division by 0 or kind of going beyond your floating point arithmetic limit. Okay. So you output VT. Okay, so that's it. That's power iteration. Oh, yeah, you're right. Thank you. This should be out. Okay. All right. So it's simple enough algorithm, just working from things. And it's a very, very important algorithm. I would say it's very, very useful. Okay. Yeah. Right. But it's unlikely that your random vector will be in the null space. So maybe I misunderstood your question. Right, but it's very unlike, that's why we're picking it to be random vector, right? So random vector, as long as the null space is not full dimensional, you will have some component in the top singular vector direction. We'll talk about that in a second. Basically, what happens is that you can show that with very high probability, you'll have at least correlation like 1 over root d. Okay, random vector will have correlation 1 over root d, and that's good enough. Okay. Yeah, but that's a good point. That's one reason why we picked a random vector without having to figure out, what's the null space. But it's quite unlikely that you will hit the null space or be very close to the null space. Okay. So, this is simple enough algorithm. What can we say about it? So the ideal thing would be to say somehow that the power iteration after so and so steps will give me a vector which is this close to the right singular vector. Okay. And that's not quite true. But what we can say is the following. So let me first state it in words. Pi will converge to a top right singular vector. Okay. Meaning, so if I run it for roughly log of d over, sorry. Okay, suppose I ran it for these many iterations, some log d over epsilon iterations. Then we want to get very close to the first principal vector, first principal component, or first right singular vector, right? And there are two ways to quantify how close you are. The first one is to say, remember, one definition of first principal component was that it maximized x times v. Right? Among all unit vectors, the first PC maximized this. And because of the magical properties of SVD, as we stated, the max over all of these things should be sigma 1, because v1 is the answer. We know x times v1 is basically sigma times u1, so you get this. Okay. So one thing we can guarantee is that if I ran it for like log d or epsilon iterations, I'll get a vector which gets close to this maximum value. If you think of it as like optimization function, I want a vector v which maximizes this ratio. Then I'm going to find a vector which maximizes this up to some small factor. Okay. So meaning, so we'll have a vector such that with high probability, with high probability over the initial random choice, this is at least 1 minus epsilon times sigma. Okay. So the maximum possible value is sigma 1, and I'm finding a vector which is at least like 1 minus epsilon times sigma. All right. So V1 is the first PC, maximizes, let me put a bar here just so that we don't confuse with the VIs as we defined it. Okay, so this is the first notion of convergence to the first PC. I'm finding a vector which is actually getting a value which is close to the maximum possible. Okay, that's good. But you can also ask, okay, I want my vector itself to genuinely be close to the first principal component. Can you even get that guarantee? Okay, not just the objective value or this, x times v norm is high, but is VL itself as a vector close to the first principal component? Okay, so that's actually more important in applications. Like, for example, when you're trying to do low rank approximation, I really want to be close to the VIs. Okay, and you cannot guarantee that in general because singular vectors are not even unique. Right? If sigma 1 and sigma 2 are the same, then V1 and V2 are kind of interchangeable, and any sum of them rescaled is also will also give you the same sigma. Okay. But what we can actually show is the following. Suppose I look at whatever this 2 factorization is. I can plot its singular. I'm just drawing like a bar chart of the singular value. Okay, and maybe the first one is sigma 1. Think of it as like a 1. Okay, no, this is 1. Let's say the next one maybe is also very close to 1. This is like 0.99. Okay, so then somehow I might not get V1 itself. I might get something like V2 unless my epsilon is very, very small. Both seem very, very good, right? So this is sigma 2 and so on. Okay, so they keep on decreasing. So the claim that we can actually make is keep going until you find a sigma which is noticeably smaller than the first one. Okay, so this is 0.99. Maybe the next one is also 0.98. But at some point, you dropped to 0.8. Okay. So keep going down like this. And let's say that's the first time that happened. So sigma m is less than 1 minus epsilon times sigma 1, but sigma m minus 1 is greater than or equal to 1 minus epsilon. So you have some threshold epsilon, and then keep going until, relatively speaking, your singular value has dropped by that much. Okay. Maybe it's the 10th one, maybe it's the 100th one, but wherever that happens, that's what you're looking at. Right? And actually, maybe let me just write it this way. Okay. And then SM be the span of V1, V2, all the way up to V. So I'm saying, look at the span of all of the singular vectors whose corresponding singular value is at least 1 minus epsilon times the largest. Let's say my threshold for epsilon is 0.01. Look at all of the things whose singular value is at least 99% of the top. Right? In some sense, I don't care about which one among these you out, because my epsilon is my tolerance threshold. So within 1%, I don't care. So any of these would be okay. All right. And that's exactly what you can show. Right. So what you can show is that if I run power iteration for L steps, where L is roughly, log like 1 over delta by epsilon. And whatever this delta is, we'll make precise in a second. Then the vector that we output is almost entirely in this span. So in particular, whatever we output, it's very close to the span of the first m singular vectors. It might have some component which is outside, but the error from this span is going to be at most L. Okay? So it's basically decreasing exponentially as you run for more and more iterations. So if there's a gap between first and second, this is saying that you're actually very close to the first singular vector. Okay? But if it's not unique, if the first and second are close, I'm going to find something which is very close to the span of the first and second, which makes sense because everything there can be a singular vector. You cannot get around that. It's not unique. Okay. Any questions about the statement? As usual, algorithms are more important, and then the bounds are more important, and then the proofs are important. So the algorithm should be clear, and the statement should be clear. Okay? So there is some ambiguity, which is unavoidable, given that SVD is not unique, but we are able to converge to the span. All right. Yeah. Yeah. Right. So, the reason is that in some sense, we've been talking about principal components as single vectors, but when the singular values are the same, it's really a whole subspace, right? So if you take identity, for example, if your matrix is identity, every vector is a principal component. There's really no compression, nothing you can do. If you take identity matrix, every vector is an eigenvector, every vector is a singular vector. Okay, so there's, in that sense, any vector is an answer. So all we're going to say is, okay, I can get you something which is in the span. Yes, exactly. Yeah, you have to project those things out and then run this algorithm as well. Okay. All right. So, we'll prove some version of this theorem. I won't prove the general version where, the first m are close and there's a gap between m and m plus 1. We'll just do the version where there's a gap between 1 and 2. Okay. The general version is basically the same idea. You just have to kind of, keep track of m other numbers, and it's a little bit more tedious. Nothing else changes. Okay. If you're interested, there are very precise formulas for how this angle changes. Okay. People have figured out exactly what's the right potential to track and how this angle changes, and you can plot it, and it miraculously almost always agrees with the theoretical ones. Okay. But before going there, I want to talk about something else. Some other nice properties of power iteration, which I think are worth understanding. Okay, so what are those? So, uh, so imagine for whatever reason, I give you three matrices, x1, x2, and x3. Okay, these are three separate matrices. Maybe each one is, let's say, 100K by 100K. They need not even be square, but let's say they are square for now. Right? And somebody says, okay, here are three matrices, but for whatever reason, I care about computing the first singular vector of x1 times x2 times x3. It's kind of made a puzzle, but it'll illustrate a very important point that is useful in practice. So suppose I have matrices x1, x2, and x3, and our goal is to compute, the first singular, let's say the first PC of the matrix x1 times x2 times x3. Okay. What do I do then? Well, I could, I know how to compute the SVD of any the first principal component of any matrix using power iteration. So I can just multiply them and do it. But is that what you should do? You think that's the best way? No, right? Because once again, multiplying matrices is something that I hate. And here, I definitely, it's like seems very wasteful. Okay. So this is the important point about power iteration and where it goes even beyond full SVD computation. That you can actually compute the first PC without even computing the matrix X. Okay. So the reason is that, technically to run the power iteration, what do I need? I need to compute X transpose times X times this vector Vt minus 1. Okay. But I can expand this out. This is just x1 times x2 times x3 transpose times. Okay. So this is and I can once again use associativity to the rescue. So I can run the whole power iteration without even computing the matrix X. All right. So to run power iteration on X, I only need a way to multiply vectors with X. Okay. I don't even need to write down X. As long as you give me some subroutine, some handle to compute X times V for any vector V, then I'm good. You can, do the transpose for that. Okay. Yeah. X transpose V2, but yeah, you can do the transpose of that maybe. Yeah, you have to be able to multiply on the left and right. Yeah. Okay. What does this remind you of? It should remind you of something that we did long ago. Like somehow I can run an algorithm as long as I can do something else. It's like a meta algorithm almost. What does it remind you of? Like gradient descent, right? I can run gradient descent as long as I can compute the gradient. Okay, I don't care about where it came from. In the same way, as long as you give me a subroutine to compute the matrix vector product, I can do it. Okay. All right, that's one thing. And the other thing I wanted to do, hold on a second. Okay, so the other thing is once we think of gradient descent, you should also think of the next step, which is to try and use acceleration. Okay, so the same thing that happened for gradient descent can also happen. Right? So you think of power iteration as kind of a version which is like plain gradient descent, right? And so like the convergence rate is like 1 over epsilon, right? To get epsilon close, you need convert, like, number of steps is like 1 over epsilon, right? And we saw the same thing earlier, like, for quadratics, for instance, if the gap was epsilon, then plane gradient got us 1 over epsilon. Whereas if we did acceleration, we could get 1 over square root epsilon, right? And it turns out you can do that even here as well. Okay, so you can talk about pi plus momentum. There's a name, the technical, the real name for this would be like Lanczos iteration. Okay, and there's some careful step sizes and so on, but at the end of the day, you kind of do the same thing as before, which is, pick a random unit vector. I compute this x transpose x times Vt minus 1 bar, just as we did. But then you also add a momentum correction, right? Which is some, beta L here. Okay. And of course, after every iteration you normalize, so you get this. Oh, sorry. I think I was right the first time itself. This should be minus 1, minus 2. Okay. You can incorporate a momentum term kind of to get acceleration. And, power iteration has convergence, which is roughly 1 over epsilon, if there's an epsilon gap, or if you want to get epsilon close to the objective function, then it has like roughly 1 over epsilon rounds. Pi plus momentum gets you 1 over square root of epsilon. Okay. Make sense? Any questions? So you're using the same idea that, somehow I use the history of the previous gradients to do something. Right? And Okay, the other trick that I want to talk about is, when we discussed earlier about computing the first principal component and second principal component and third principal component and so on, we said, okay, compute the first one, then you kind of, project it out, and then compute the second one, project it out, then compute the third one, and so on. Okay? But that's like really, I think the theoretical bounds will be the same, but when you run it, it's going to be much slower than trying to do something like computing all of them together. Okay. So what does that mean? Again, there are various ways to do it. So I'm just going to give the high level idea, which is computing top K. Okay. So what you should do then is somehow keep track of a subspace, which you think is going to be the span of the top K. Okay, so start with V01, V02. Maybe let me put these things on the superscripts. Okay, V01, V02, V0K, which are all orthonormal. Okay. And then you compute for P equals 1 through L. Okay. In some sense, I want to keep track of all K at a time. And then what do you do? Remember, we want orthogonalization everywhere, right? So the first K should be orthogonal, otherwise I'm not doing, I might get the same vector repeated, okay? So what do you do then? Basically, you run Gram-Schmidt orthonormalization on these vectors, okay? So you said V1t, comma, VTK is orthonormal. Okay, there are various ways to do it. Basically, you look at the span of these things and find an orthonormal basis for that subspace, and then you iterate. Okay, this is called subspace iteration because in some sense, I'm manipulating the subspace of the first K things. Right? And the convergence to this will depend on the gap between the Kth and K plus 1. Okay? This is like, subspace iteration. There were many, many variants of this. All right? Okay. And the other thing, that people also try and do is, so remember the convergence of SVD depends on the gap between the first and second, right? So now, let's say for whatever reason, someone said, okay, I want the first and the last singular vector. Okay, some crazy person comes and says, okay, I don't care about the second, but I want the first and like the last one. What do you do? Yeah, last non-zero one. Again, we're talking about heuristics. You can actually make it formal, analyze it, and there are ways to pick out the right thing. But just let's play around with this question, right? Question. Actually, let's say give me the last non-zero. BC. What can you do? You have to compute. Do you really need to compute one at a time, or can you do something? Any guesses? Yeah. No, but that's very expensive, right? Inverse is again, it's even more expensive than matrix multiplications, which we want to avoid. Yeah. I mean, that's one way to compute the inverse, really. Compute all of them, and then that will give you the inverse, right? So what's it, but I want only the last one. I don't care about everything before. So what would you do? Again, just think of heuristics for now. We can make it formal, analyze it, but let's put on our hacker hat. Guesses? No, yes. Okay, so let me give you a hint, right? So suppose I tell you that, okay, so we have, for whatever reason, I even gave you Y, the matrix X transpose X. And what was this? This was sigma 1 squared times V1, V1 transpose plus sigma 2 squared times V2, V2 transpose plus. Yeah, so we want to reverse the sigmas, but how do I do that? No, but to do the reciprocal, I don't know these individual sigmas. I only know the Y. Okay. So, this is a trick that's actually useful, not just for computing the smallest one, but also for kernel problems and so on, is, what I can do is, for example, compute sigma 1. I don't even need V1. I just need to compute sigma 1. Okay, I computed the largest singular value. That I can do. Power iteration, assuming there is a gap, will give me something like this, right? And then I'm just going to do, let's say I compute this matrix. Oh, that's a number minus a matrix. That doesn't make sense. But this matrix makes sense. Okay, so this is identity minus 1. Okay. What is this going to do to the singular values? It will shift them all. So, as an identity, this is basically 2 sigma 1 squared minus sigma r squared times, okay, let me write it down properly first. So let's say Y is full rank for now. Okay, so I'm computing the smallest one. Otherwise, you can do the same thing by some other tricks, but let's say it's full rank. Then this is just okay. But what is the top singular vector of this matrix? The last one. I effectively reversed it, right? Okay, so you can, do these kinds of tricks. And, one place where people actually do this trick, even for computing the top k, is you can transform the matrix so that you amplify the gap, okay, by using polynomials, and that's a very important trick in practice. Right? Yeah. Anything bigger, yeah. Yeah, yeah. Actually, you can do that too. Yeah. Yeah. So you just want to reverse it. So, you're just subtracting it up. And, if you make it too big, some of the gap might be small. You might pay because of that. But if you do this, somehow it seems a little bit more efficient. Okay. But anyway, this is just a heuristic, right? You're not analyzing bounds. But, people have figured out how to kind of manipulate things so that I can pick out, like, let's say someone says, okay, here's number 0.7. Give me the singular value which is closest to 0.7. What do I do then? Point is, you can do polynomial operations in the matrix, which correspond to polynomial operations on the eigenvalues to create gaps so that 0.7 is the largest. Okay, and then you repeat. Okay, so that's what I wanted to stress. Like, somehow you can pick out each one if you wanted. So that's why power iteration is more useful, not just because you can compute the largest one, but it has so much versatility in it. You only need to be able to do matrix vector products. I can play tricks like this to, even figure out the smallest one if I wanted to. If you ask me to figure out the one which is like closest to 0.5, I can also do that by playing tricks where I shift, scale, and do some other things. Okay. And pretty much every numerical linear algebra package, like NumPy, LayPack, and so on, will have all of this implemented in it. Okay? And there will be versions which don't even ask for a matrix. They'll ask you for a function handle which gives you the matrix vector form. Okay, so in fact, that's how, if you're working with very big matrices, that's what you would do. People have optimized these things extremely well, like writing the for loops, how to manage memory with these things, and so on. So you would never implement power iteration from scratch, even if you want to do these strings, even if you want to use these tricks. You would implement your own handle for computing matrix vector product and pass it on to these packages. And things like LayPack and so on, which are extremely optimized, still written in Fortran. And at some point when I was in grad school, I had to look up Fortran code. It was very painful. Okay. All right. So lastly, I want to connect to one other thing that we did, which was to the Netflix challenge again. Okay. So there we said, okay, I have this matrix X, huge matrix, right? Big, big matrix, very sparse, right? Only 1% entries known. Okay. And we said one approach to kind of guess the missing entries, it was to compute, so let me say pre-process, centering, scaling the variance, and so on, compute best rank K approximation, post-process. Okay. And this is basically means that you're computing the top K SVD of some matrix. You can do this with and get 4% improvement. Right? And for this, you would definitely use the extremely optimized versions. You would just say, okay, here's my sparse matrix. I'm not going to write down X. There's a compact way to represent this X. It's not written as this n by d, like rows and columns. You use a sparse matrix representation where you only store the non-zero entries. Okay? Or unknown, or the known entries. Right. So another way to think about this is, okay, what are we interested in? You can imagine, okay, I have some true ratings matrix X star. And what are we trying to do here? I'm trying to imagine that X star is a small rank matrix. Even if I guarantee you that X star is a small rank matrix, I cannot compute the missing entries because I only see some of the entries. Okay. So one optimization problem I can write down is the following. My goal is to minimize the okay. Give me a matrix which agrees with the seen entries as much as possible while being low rank. That's a good sort of abstraction of the ML problem that we are trying to solve. If someone said, okay, here's a matrix, I'm giving you some entries, guess the remaining entries. My abstraction for that is to solve the following optimization problem, which is while let's say rank of X tilde is less than or equal to 30. Okay. So the 4% improvement, you can think of it as a heuristic for this optimization problem. Okay. We said our first cut is, okay, I don't know the full matrix, so I'm just going to put zeros or the averages in the remaining and do SVD. And that's a rank 30 matrix that gives me some value here. Okay, but that might not be the optimal solution, right? In fact, it's most likely not the optimal solution. Okay. But this is an optimization problem. When I say an optimization problem, what is something you can try and do? We can try and do gradient descent, but there is a problem. What's the problem? Yeah, we have a constraint. It's not convex. Okay. So first, it's a constraint optimization problem, and it's not convex, right? Okay, forget convexity for now. But if it's a constraint optimization problem, I don't, I'm still running it mainly as a heuristic, or I want to see how it does. What can I do? But how do you, but the rank is a non-smooth function, right? So how do you compute the gradient? Yeah. Exactly, right? So, so that actually is a paper that we wrote long ago. It's called singular value projection. Okay. So what we're going to do is, this is a special thing about the rank constraint. It's a non-convex set, but it's one of the few non-convex sets onto which I can actually project. SVD is solving a highly non-convex problem, one of the few non-convex problems that we've been lucky that is solvable efficiently. Okay. So basically, we can do projected gradient descent. Right. So we have this rank 30 set. You can actually plot these things and it looks crazy. It's something scary like this. Okay. But I can always project onto this set. The projection operation is efficiently computable. Okay. And when we come back, I'll talk about, I'll describe this algorithm in full. It's just a few lines. Basically, you compute the gradient. After each iteration, you project back onto the set of rank 30 matrices by doing SVD. Right. That's a different algorithm that takes you to something like 5.5%. Okay, it boosts this 4% to like 5.5 or something between 5.5 and 6. And it has very nice theoretical guarantees. We call it singular value projection because you're basically projecting after doing the SVD. And you can show that it satisfies, it can do low rank recovery with the very few measurements and many other nice properties. Okay. All right, so let me stop here. And remember, Monday, the assignment is due, and Wednesday is the exam. So, make sure you're caught up on all of this stuff. If you have any questions, just keep asking. All right? Okay, I'll see you all on Monday.